Hello again. In the previous video I attempted to fix this scope and I failed. And in today's video I want to take a closer look at the high voltage multiplier that apparently failed. And as it turns out, removing the high voltage multiplier is a challenge in itself, because everything that is in this back area of the scope is very inaccessible. Okay, so apparently there is a trick to this, but it took me so long to figure it out. So you have to remove these two screws and then this piece of aluminium slides out. And with this thing out, you're one step closer at removing the high voltage multiplier. Obviously you have to remove the high voltage connection first, and then the high voltage multiplier can be easily removed from the chassis. So here it is. So here's a close-up on the high voltage multiplier, and as you can see it's very dirty, just like anything else on the high voltage side of this scope. Unfortunately, high voltage components are really inconvenient to test. That's because you cannot tell whether or not they are okay just by testing them with a multimeter. Let's have a look at this for example. I will connect the negative probe to the ground and the positive probe to the transformer input or AC input, and we get nothing. Same goes with the high voltage output. The only thing we get is some capacitance between the two terminals, so we cannot say much about this. There is no way to tell whether or not this is okay or not, unless you get creative and make some sort of test bench for it. Since I have a curve tracer, I decided to connect it to the curve tracer as well, because this will identify any shorts. So let's see what happens. We are at 20 microamps per division and 100 volts per division. I also have this ground wire here connected to a glass rod just in case, and this is for safety reasons, so that I can short out the output so that it doesn't shock me when I remove it from the circuit. Let's slowly increase the voltage to see what happens. So far so good, it looks just like a charging capacitor through a diode or something like that. And we can go all the way up to 1 kilovolt and it still looks okay. So it's drawing about 10 microamps, which is probably acceptable because the diodes and everything have some leakage. Let's short it out to see what happens. Okay, looks good to me. So with the output shorted, it looks oval, it's almost like a capacitor or something like that. And as soon as I remove the short, I can see it charging up once again. So weirdly enough, it looks totally fine to me. I don't think this is the issue. And by the way, look how much my desk lamp is messing with the curve tracer. This is so frustrating. It really makes me wonder how this crappy design actually passed any sort of EMC testing. This is beyond me. Anyway, this is how you safely remove the multiplier from the test bench. So first of all, the collector supply needs to be at 0, then this switch needs to be disconnected just in case, and then you have to ground the output. Maybe you can ground the input too, but it doesn't make any difference because it's disconnected. Make sure you short it out before removing it from the circuit. So now I think it's safe to touch. At this point I got really paranoid and I thought about checking the CRT as well, at least the post-acceleration anode. So I want to test it up to 1000 volts to see if it's shorted or anything. Probably not, almost certainly not, but let's see. Okay. That looks nice. It looks exactly like a capacitor, so nothing surprising here, so I guess it's okay. We are at 10 microamps per division and 100 volts per division. After a few tests, I made some unexpected progress. So I decided to look at the waveforms in the high voltage power supply to see if it's working properly or not without the high voltage multiplier, because I assumed it to be shorted or something like that. And the waveforms were pretty much okay. The frequency is bang on, and it looks like the high voltage power supply is driving the transformer a little bit too hard. So the amplitude of the sine wave on the collector of the power transistor was about 50 volts instead of 38, which is, I guess, acceptable. So I decided to connect the high voltage multiplier to see what happens. And to my surprise, it works. So the setup is very sketchy and I wouldn't recommend doing something like this. I have a grounding rod here for safety and everything else is connected with jumper wires, which is something that you should never ever do. And the Tektronix 466 is still connected to the primary of the transformer. Let's power it up to see what happens. So I can hear the distinctive high voltage sounds. The waveform looks okay. I still have no spot on the CRT. And nothing is arcing, so that's nice. So with the high voltage power supply off, I can confirm that it works by shorting it, which is once again not a good idea, and I hope it doesn't kill the multiplier, but I have to do it for safety reasons anyway. So as you can see, the high voltage multiplier is definitely okay. So the issue is somewhere else. Now I changed a few things here, to be honest, and maybe they changed something or not, I'm not sure. So I tested every single transistor in the high voltage power supply. Maybe moving the transistors inside the socket made a difference, I don't know. And I also removed the plugins, as you can see, which could also make a difference, even though I don't expect them to make a difference because they are not connected to the high voltage power supply. So let's put the plugins back in to see what happens. So the time base is back in. I decided to put the plugins back in one by one. Now let's give it a try once again. Still no spot, but the high voltage is definitely working, so I don't know. Let's put in the vertical plugin also. Okay, so both plugins are in. Let's see what happens. High voltage is on. Still no spot. But weirdly enough, it looks like the high voltage is working, and it's also drawing less current than I remember, so I think it was drawing around 400 milliamps. I don't know what's going on, this is weird. Now, using the sacrificial meter, once again, I will try to adjust the cathode bias for minus 2.5 volts. So the cathode bias maybe is too large because the meter is pegging. Let's see if I can adjust it. And I can. And it looks like about here we are at minus 2.5 kV. So I would say the cathode bias is okay. Weirdly enough, the current consumption got lower. So now I will try to adjust the grid cutoff as well to see if it helps. Maybe we will get the spot back. And we don't. And weirdly enough, the grid cutoff changes the current consumption of the whole thing, which is something quite strange, I would say. And from one end to another it does nothing. Now I have some big news. I finally have the first signs of life here. So what I did off camera was to try to measure the G1 voltage as well, which is also about minus 2.5 kV. And weirdly enough, with the meter connected to G1, actually between G1 and ground, the CRT started flashing something at startup. Let me show you. So the scope is on except for the high voltage power supply, which is still powered externally from the lab bench power supply. And now I will turn on the high voltage as well. And as you can see, it does something at startup. and also when it turns off. So what I think is happening is that the blanking amplifier is still not working, but for some reason the high voltage power supply started to work normally. So I think it's time to look at the blanking amplifier once again and probably stop doing sketchy stuff with the high voltage power supply and put everything back. Here's a closer look at the output of the blanking amplifier or the bright up board. Basically what the manual says is that the lower level should be at around 6 volts, and I don't have specs for the upper level, so in my case the lower voltage is at around 6 volts and it swings all the way up to around 60 volts or so. So here we are at 20 volts per division. So I think the bright up board actually works with my replacement transistor, even though the frequency response may not be perfect. As you can see, the waveform is not a perfect square wave. I also noticed that with the high voltage power supply on, by measuring the G1 voltage with the old meter, the scope pegs the meter, which didn't happen with the cathode because I got it right at minus 2.5 kV. So this means that the scope holds the first grid at a more negative potential than the cathode, so basically the tube is in cutoff, so it doesn't display anything. To test this theory, I connected the old meter on the 500 volt range with the negative probe to G1 and the positive probe to cathode. And with the high voltage power supply off, G1 is already more negative than the cathode by around 100 volts. So the tube is in cutoff. Let's turn on the high voltage power supply and see what happens. Okay, so now the grid is even more negative. It's at around minus 150 volts with respect to the cathode, so that's why we don't see anything on the CRT. And now I'm trying to adjust the grid cutoff once again, and as you can see it does nothing, so there is something wrong with the high voltage power supply. Look, this is the grid cutoff, it goes from one end to another and the grid voltage doesn't change. The grid voltage with respect to the cathode. So I kept looking at the schematic for a possible cause for this, and I noticed a cap that could cause some issues on the grid bias supply, which is this one. I think this one is critical for a correct grid bias. So what I did was to solder another capacitor in parallel to this to see if it helps or if it makes things worse. I know this is not the best thing to do because the capacitor could be leaky, and in that case it doesn't help. And to see what happens from the back, I did what any repairman would do, which is to put a mirror in front of the CRT. So let's see what happens. Okay, it didn't do much. I think it's pretty much the same thing. Just to be safe, I removed the old cap from the circuit and I only left the new one in place, so let's give it a try once again. Maybe it helps, I don't know. And I think the high voltage doesn't start up anymore, which is weird. Oh. Something's arcing, I think. So I just did something really stupid. One of the test leads shorted out G1 to the cathode. That's why we heard some arcing, but the circuit is just as dead as it was before, so nothing bad happened. So I set up a different experiment where I disconnected the grid bias diode completely. So now we should have no grid bias, which I think would turn the CRT fully on. Let's just hope that nothing arcs around the diode, and let's give it a try. And we get nothing on the CRT. This is not what I expected. That's pretty weird. So by doing this experiment I finally found the issue. It looks like there is no cathode bias, and apparently everything was powered by the grid bias supply. Due to the clamping diode that exists between the grid and the cathode was negatively biased through the grid bias supply. That's why we saw something on the CRT, and that's why the CRT was always in cutoff. So now with the grid bias supply removed, there is no high voltage on the cathode. So that explains why this is not working. So once again, the sacrificial meter, as I like to call it, is on the cathode. So it's measuring the cathode voltage with respect to ground, and with the high voltage power supply on, we get 0 volts. That's because everything was powered by the grid bias supply. And now I feel really stupid about this, but the reason was hiding in plain sight. Do you see what I see? Look at this. The pin of the diode was broken. So it doesn't make contact here, so we have no cathode bias. It took me about 3 days to find it. Now unfortunately I don't have the proper replacement for that diode, so since I'm eager to see if the scope works, I decided to use one of these black and white TV high voltage diodes, and I prepared one like this. So I have a piece of high voltage wire on one end and I have a terminal on the other end. So the terminal goes back into the PCB and the high voltage wire goes to the transformer. And we are supposed to get a negative voltage on the PCB. That's why the anode goes to the PCB and the cathode goes to the high voltage transformer. Okay, the diode is now installed. It looks as ridiculous as you'd expect. Let's just turn it on and hope that nothing arcs over. So I would expect to have a full brightness on the CRT. Okay, the moment of truth. 3, 2, 1. Yes, it works. Nice. So we finally have a trace on the CRT. Let me give you a better look at that. So we finally have a trace. And now I also reconnected the grid bias diode. And now I have to readjust the voltages and make sure we still have a trace. So I will start by adjusting the cathode voltage once again. Okay, so we don't have a trace anymore, but maybe that's because the voltages are not right. So I will readjust the cathode voltage first of all. We need to be full scale on this meter, which is unfortunately out of frame. So it looks okay. We are at minus 2.5 kV now. And we have to do the same thing with the grid. Okay, so the meter is now on G1 and I will look for the voltage there and I will try to adjust the cutoff until we get a picture. Okay, so we are more than full scale, so the grid is more negative. Let's see if I can now adjust the voltage. And for some reason I cannot adjust the voltage, so from one end to another the voltage is still too high. Which means that the grid is more negative and we cannot get a trace once again. The cause for this is the fact that now we have two different types of diodes which have different voltage drops, so the voltages on the G1 and the cathode are not equal since they are generated by different power supplies basically. So to make everything work as a temporary fix, I readjusted the cathode voltage and now I get the trace back. So as you can see, we have the trace back, and by adjusting the cathode voltage we can make it dimmer or brighter. That's because as we are adjusting the cathode voltage we are basically balancing the cathode and G1. Let's leave it like this for a while. And now that the high voltage power supply is working, let's test it with a signal at the input. Nice, we finally have a sine wave. Let's see if we can focus it. We sort of can focus it, okay. So the picture is much smaller than it should be, which is to be expected because the voltages are not right at this point. We have vertical control, that's pretty nice. What about horizontal? Let's see, position, okay. We have control on the horizontal axis as well. Fine, position adjustment, 10x. 10x looks okay. Time base, what about the time base? Okay. So it only works with this knob cranked all the way up. And finally, another important test is to see whether or not the scope can power up its own high voltage power supply. Because until now the high voltage power supply was powered by this external lab bench power supply. So now the high voltage power supply is connected to the internal 30 volt rail, and we are seeing the current on this multimeter. And it looks like the high voltage is still working. So let's check the voltage as well. And the voltage is around 27 volts. So now I think we can order the parts for the high voltage power supply and finally fix the scope. Now through the magic of video editing, the parts are already here. And the high voltage diodes are in. Let's see if the scope works now. We don't get anything on the CRT. That's probably okay. And now we have to adjust the voltages once again. So I have an adjustment tool right here. It's a plastic one to make sure it doesn't shock me. And I will adjust the cathode for minus 2.5 kV. And that's okay. So after adjusting the cutoff, it works, but it has no blanking. And it has full brightness and no brightness control. So I defocused it on purpose so that it doesn't burn a hole into the CRT. So back to the blanking amplifier. Unfortunately, I don't remember what settings I used the last time I saw it working, but I know I played with the settings, especially the time-based settings. So now it doesn't look like it's working okay. So you have about a 5 volt offset or something like that, but the pulses are only about 1 volt. So the amplitude of the pulses is too low. Let's see if it works with the other transistor. Unfortunately, the transistor didn't change much, so this is back to the NTE 159 that people recommended on the forum, and the waveforms look exactly the same. Yeah, I think I got it. So the differences are due to the changes in intensity settings. So look, here we are at full intensity, and now I'm lowering it. And here we are at 0 intensity. So this is what makes the difference. So you have to be at full intensity to see a high amplitude on the scope. Okay, so I think the amplifier's worst case is when the time base is cranked all the way up at the highest speed. At the highest speed and at reduced brightness, the amplifier has an overshoot, which is actually visible on the screen. Let me show you. So you can see that the trace is not uniform, and I know that the blanking amplifier has an adjustment for this, but before adjusting it, I'm curious to see which transistor performs better. So for comparison, this is the NTE 159. Okay, the moment of truth for the Japanese one. Let's see. 3, 2, 1. This one is weird. It looks like it has some sort of high frequency oscillation. And by moving the probe, it doesn't do that anymore, so I'm not sure what to believe now. Because the frequency response looks better, it has a less overshoot. It's much faster. but with the scope probe in a certain position it starts to oscillate. I'm not sure what to do. So I'm back to the NT transistor, and as you can see I have some ringing, but I think by shortening its leads I reduce the ringing actually. It looks slightly better now. And this ringing is also visible on the CRT because the trace is not uniform. So what I need to do is to adjust its frequency compensation capacitor to get rid of the ringing. So what I'm doing is I'm using this screwdriver to adjust the compensation capacitor of the bright up board. You should really do this with a plastic screwdriver, but I don't have any. I mean, the adjustment tools that I have that are plastic are not able to turn the capacitor, and I already broke one. And here's how the waveform looks like for various settings. Let's play with the capacitor a little bit. So the capacitor is all the way out, probably at its minimum, and the ringing is pretty high. You can see it on 10x also. And I think by turning it in just a little bit we can compensate for that. But we have to remove the screwdriver before assessing the waveform. Okay, it's in just a little bit. Let's turn it some more. Okay, that's getting close. Maybe turn it just a little bit more. Maybe go back just a little bit. Too much. Okay, I would say that's close enough. And of course the trace looks perfect now. And now let's get back to the high voltage power supply. I'm so sorry that I'm jumping from one circuit to another, but at one point I didn't know which one causes the fault. Anyway, here's my inrush current limiter. This is the old one, and let's just hope that the new one lasts for another 50 years. And here's how the power supply looks like after I worked on it. I thought it would be a good idea to change the electrolytics as well. Here's the new thermistor in place, the new high voltage diodes, and I also cleaned it with isopropyl alcohol because it was really dirty and it had flux residues. I tested it, it works, and I think now it's time to put the high voltage multiplier back. Since the high voltage components are really dirty, I think the first step is to clean them up with some isopropyl alcohol. Okay, I think that's better. And now I need to do the same thing with this female high voltage connector. Now we are talking. I think the only reasonable way to remove the high voltage multiplier is to remove this high voltage connector, so now it needs to go back. First of all, this plastic jacket, and then I have to reconnect the pin or the contact. I will let it cool down because I don't want it to melt the plastic. I will recheck it to make sure it has no sharp points because we don't want any corona forming from it. And now we can put the plastic jacket back. Yeah, I forgot something is not supposed to come out. Yep, it had this washer as well. Okay. I think it goes something like this. Yep, looks good. So now we just plug it in and adjust the wires. Yep, sounds like it's making contact, and now we need to secure the wires back into place with these things. And the high voltage wire is back in its place. And here it is. Let's just plug it in and hope that we did everything right and that nothing arcs. Finally. So it looks like it's mostly working, but the trace is very unstable from time to time, and I don't know what the cause of this could be. As you can see, it's jumping around, and also it doesn't cover the entire screen from left to right. So there are some things that we still need to fix, but it's mostly okay. So to fix the horizontal section, the first thing that I did was to check all the voltages once again, which are accessible right here. And the voltages are bang on, which is impressive for something that is this old. Then the next aspect would be the horizontal amplifier, because it has some adjustments here that could get dirty over time and cause some intermittent issues. So let's check them. So let's clean the trimmer pots with some isopropyl alcohol and turn them just a little bit to see if the issue goes away. The moment of truth. Let's see what we get. Okay, let's see. Looks like that fixed it, because the horizontal size is okay now. It covers the entire screen. Let's see if it still jumps around. And it doesn't, so that's great. Nice. The waveform is finally stable. The only downside to this fix is that this ruins the calibration. And to calibrate it, you normally need some specialized fixtures, which I don't have, so that's a bit of a pain. But I will do my best to calibrate it against my Siglent oscilloscope, I guess. So to conclude, this was a pretty difficult repair because the scope had multiple issues. First of all, we had smoke, which was due to a shorted transistor in the blanking amplifier. Then we had no high voltage, which was due to a blown out thermistor and a broken leg on one of the high voltage diodes. And we had some horizontal issues, including stability issues and wrong horizontal size, which were due to dirty trim pots. To be honest, I only fixed this scope for my own pleasure and for views and likes, so if you like this video, please give it a thumbs up, and if you're interested in more content related to electronics and programming, please subscribe to this channel because there is more content like this on the way. That's it for now. Bye.